Hello, welcome to your second fully vodcasted lecture. If you're watching this on the regularly scheduled lecture time, then it is Monday, March the 4th, and you're looking towards a homework being due tomorrow on the 5th. I do have my office hours today online on Illuminate, so you can catch me on Illuminate from either 2 to 3 p.m. or from 7:30 to 8:30 p.m. Either time works great. Also remember that you can get help from Callie or many other of the teaching assistants if you need it tomorrow during lab. In terms of lab, I should mention that perhaps what's foremost on your mind is that we do have a practical exam coming up. You'll have the practical on Thursday, and in terms of the skills that we're going to be asking you to show us on that practical, we'll be looking for you to focus a microscope. We'll also be looking for aseptic pipetting technique and T-streaking. Of course, we're going to have you streak. So in terms of focusing the microscope, everybody thinks that sounds like a really super easy skill, but in fact when you get in there, this ends up being the hardest one. Don't forget that anytime you get ready to focus a microscope, make yourself a focus line. Start on the focus line, it saves you time. Then you can move on to the smear. Make sure that the bottom of your slide is clean and that you're not accidentally focusing on something on the bottom of the slide. And make sure that you do get good focus on 10x and then move up to 100x. In terms of aseptic pipetting, when in doubt, flame it out, and don't forget the tips and lips. If you remember that rule and you watch this on Virtual Edge a couple times, I have a feeling you're going to rock it. In terms of streaking, we'll be looking for several different things. We'll be looking for your ability to get an isolated colony, meaning that you need to be able to flame in between each one of your areas in order to get that done. We will also be looking for your aseptic technique, the when in doubt, flame it out rules. And finally, we'll be looking to make sure that if you take your original culture from a colony, that you do use a single isolated colony. Remember, that's the only way that you have a pure culture. So a lot of things to keep in mind as you head into the practical exam, but honestly, as long as you've been keeping up and really engaged in lab, you're going to have fun on the practical. One note on it though, it is not a multiple choice exam, so you do need to be able to fill in the blank, you need to be able to write certain things, so that is a word of note. Sometimes that bothers people, so just wanted to let you all know. When we left off last time, we had been talking about the wild world of photosynthesis, and we had managed to get through our conversations on photosystem 1 and photosystem 2 as they described oxygenic phototrophs. Remember the ones that make oxygen? So we're going to jump right back into that coverage to kick things off today. And from there, you can look forward to a change in pace as we finish off metabolism and we head into gene expression. Rock on. Remember when we were talking about the combustion of jelly donuts? This was the reaction that we showed. So remember that reaction there. But remember that the reverse of this reaction is the one that typifies photosynthesis. So photosynthesis is the reverse of our combustion reaction, meaning that for photosynthesis it is an energy consuming reaction. And remember, you reverse the sign on that. 686 kilocal per mole will be what represents photosynthesis. So photosynthesis, rather than being exergonic, is endergonic. So let's look at how we might contrast the dark reactions of photosynthesis with the oxidation of sugar by a chemoheterotroph. So let's just write down what's true of photosynthesis. So photosynthesis is anabolic. So the dark reactions of photosynthesis, the Calvin cycle, will be anabolic, not catabolic. That is, it's a building set of reactions. It's going to be reductive, not oxidative. That is, it's going to consume reducing power, not make it. It is going to be endergonic, not exergonic. That is, it's going to consume ATP, not produce it. Okay, so recognize this massive contrast between the
Calvin cycle, say, if we contrasted the Calvin cycle with the TCA cycle, these are important ways in which we would want to contrast those two cycles. Okay, so a biosynthetic cycle is the Calvin cycle versus a primarily catabolic or breakdown pathway, which is the TCA, even though we know it makes precursor metabolites, right, that makes it amphibolic. So what other group of organisms must be able to fix carbon? We know this right off because we started there. Anything that is called an autotroph, so not just photoautotrophs, but also chemoautotrophs, are rock eaters. Excellent. Let's now take a look at the Calvin cycle. In the Calvin cycle, which here's the net reaction, the thing that I want to draw your attention to is the massive consumption of ATP, 18 of them, and reducing power, 12 NADPH, just to make one 6-carbon sugar. Holy cow, 18 ATPs, 12 NADPHs just to make one 6-carbon sugar. Check that. So let's look at one turn, or actually let's look at 6 turns of the Calvin cycle that allows that to happen, because it's got to turn 6 times in order to allow the synthesis of one 6-carbon sugar. So the input of 18 and 12, the first portion of the Calvin cycle is called incorporation. In incorporation, the inorganic CO2 molecule is brought in. This is not unlike the TCA cycle, where a smaller molecule is brought in and bonds are formed. It's a condensation reaction, it's a synthesis reaction. One thing that is different in this first reaction of the Calvin cycle is that after this, these carbon dioxides are brought in and added to this ribulose 1,5-bisphosphate, that is going to synthesize a 6-carbon molecule that is actually going to go ahead and then split down into 2 3-carbon molecules. It's sort of this just spontaneous process that happens. Some of you will recognize the name of the enzyme that catalyzes the incorporation step. It's called Rubisco. And I know, gosh, poor Josh Ladwig, this is, you know, you're the photosynthesis expert, and I know this is very trivial for you. So I apologize if it's been a boring day. Josh is your expert. If you guys have any questions for him, he's studied photosynthesis for 6 years, right, Josh? So he'll recognize the name of Rubisco, the enzyme that catalyzes the incorporation step. And notice that this then makes something that looks familiar to us. It makes a molecule called 3-phosphoglycerate. And hopefully everybody's working on their posters, their metabolism posters, and you recognize that as an intermediate of glycolysis. In fact, it's the intermediate of glycolysis that's formed in step 7 when 1,3-bisphosphoglycerate is hydrolyzed to make ATP. So look at this. These steps in the next portion of photosynthesis of the dark reactions of the Calvin cycle, they're the opposite. They're the reverse of what we saw in the glycolytic pathway. So rather than producing ATP, it's consuming it. So it's consuming the ATP, and we see it going in the reverse, making 1,3-BPG, which then can be converted using a lot of reducing power into glyceraldehyde 3-phosphate, which we also recognize, which is the precursor metabolite to make the 1,6-carbon sugar. So this step, this set of steps in photosynthesis or in the Calvin cycle is called reduction and synthesis, making sense because it is the portion in which we see the synthesis of that 6-carbon sugar. After that, look at this. Notice that I'm being simplistic here because there are many steps that happen next. So we're leaving out a lot of those. But in the next portion of the reaction, we see the consumption of more ATP just to regenerate the initial molecule with which the CO2 reacted. And in fact, this is called regeneration. So the Calvin cycle, as it turns, can be split into 3 portions: incorporation, reduction and synthesis, and then finally regeneration. So this is the process whereby the energy and the reducing power, the ATP and the reducing power made in light reactions is harnessed to finally make this 1,6-carbon sugar. A very, very endergonic process consuming 18 ATP and 12 NADPH. Wow, man, that is a great example of an anabolic pathway. So that coverage ends our consideration of photosynthesis, and it's a great segue into the next section where I want to talk more about anabolic pathways. We could spend a full semester doing that, and so my highlights here are just that. They're just highlights. But I want it with the principles in mind that we saw in the anabolic pathway of the Calvin cycle. I want to take that knowledge and apply it broadly to our large poster view and think about ways in which anabolism can run in all of these varying pathways, and maybe look at sort of a skeleton outline as we're seeing in this picture, and recognize that many of the catabolic pathways that we talked about were amphibolic, right? And that they too could generate precursor metabolites that could be used in anabolism. Let's just look at a few examples of molecules that can be used as precursor metabolites that can be used to synthesize molecules in anabolism. So if we look at the TCA cycle, steps 1, 2, 3, and we recognize that alpha-ketoglutarate is generated in the third step there. Alpha-ketoglutarate can be used to synthesize both glutamate and aspartate. So it can be used as a precursor metabolite in the anabolic pathway that synthesizes these two amino acids. Succinyl-CoA can be used as a precursor metabolite to synthesize porphyrins, important in the ETC. Also, many others of the intermediates, such as oxaloacetate, can be used to synthesize also amino acids, for example, methionine and threonine. It can also be converted backwards into pyruvate, and pyruvate can be used to synthesize glucose in the backwards pathway. So eventually, if this pathway is followed all the way backwards, we can get the synthesis of glucose in the anabolic pathway called gluconeogenesis. Many of the intermediates of the pentose phosphate pathway can be used to synthesize aromatic amino acids. Also recognize that glyceraldehyde 3-phosphate dihydroxyacetone phosphate can be used to make the backbones of fatty acids. I'm going to abbreviate that, fatty acids. Also, too, acetyl-CoA can be used to build up the fatty side chains of a fat, so fatty acid synthesis. Man, there's no end, is there? Pyruvate can be used to synthesize alanine. There are so many biosynthetic pathways within a cell, and if you want to read a little bit more of that, your text goes into even greater depth on many of those things. So feel free to take more time with this. We're simply scratching the surface, and let's take just a moment to write down what we've shown in picture view and maybe that you've added to your poster. So we'll just jot a few notes. Fatty acids are synthesized from acetyl-CoA when 2 carbon groups are added to a constantly elongating chain. It's held by a protein called acyl carrier protein, which I mentioned because it's cool. It has what's almost like a long elephant trunk that it can use to get more and more 2 carbon groups on it. Glycerol synthesized from dihydroxyacetone phosphate, the glycerol backbone, so we talked about that. Amino acids from a variety of sources ranging from the pentose phosphate pathway to glycolysis to the TCA cycle. So things like glutamate and aspartate, we talked about alpha-ketoglutarate being the precursor metabolite to their synthesis, and we talked about aromatic amino acids such as phenylalanine coming from the pentose phosphate pathway intermediates as precursors. And oftentimes in these biosynthetic pathways, you guys already know this, feedback inhibition is also often an important thing. The products, if they accumulate too much, that is, if there's too much glutamate, it'll feedback, inhibit the enzymes that are used in the biosynthesis of that amino acid. And nucleotide synthesis, man, it's so complex that we're just going to say it's really complex. And that's how we're going to leave it today in our discussion of anabolism. So today is both a happy and a sad day. It's a little bit sad because we're leaving metabolism behind. So this for you is your cue to spend some good time making that metabolism poster. And I know, Erin, you've already gotten started on yours. Feel free to use some of the posters in the lab to help you out with that process. And use me as a resource as well, and your TI TAs and your SI leaders, they can help you build the best poster possible to make it so that your third exam is the best ever, because on your third exam, you will be allowed to use your metabolism poster. Pretty sweet deal.